So we are going to explore green cellular network little more, and we have two speakers today who are going to give us in-depth understanding of what it is about. Uh, we have seen lot of improvement in these cell phone devices so far. We have so many models coming up. They try their best to optimize the battery performance, but if you see, it is one-handed, right? I mean, you are doing it all in the device level, but there is not much happening in the back end, the network level. So Nivedita and Mahima here are, going to explain what we can do to improve it at the network level. So we are looking at how to make this cellular network itself green so that it can help us in saving battery life. Nivedita is working as a software engineer in Intel Mobile Communications. She has experience in design and development of protocol stack and mobile platforms. Mahima works as system engineer in Intel Mobile Communications. She has completed PhD in wireless communication from IIT Mumbai. And I'll give stage to Nivedita. Thanks.
Thanks, Vaishali. Good afternoon, guys. It's been a terrific day, isn't it? Good. So, what are we going to talk today? We are going to talk about the new horizon of innovation and transformation. We're going to talk about the developmental changes that is going to collectively shape the future of telecom industry. We're going to talk about green cellular networks, right? So let's begin. This is our outline. We're going to begin with what's our motivation, and we'll also touch upon the 5G requirements and back it up with the technical details. Mobile phones, right? Rarely has any technical invention that has changed our lives so profound as mobile phones, right? It was just in 1991 where the first mobile phone call took place in Finland, and we are just 25 years down the line. We have 4.7 billion users today. That's more than half of the global population, right? The telecom evolution has witnessed a generations of technology, like we have seen the 2G, 3G, and 4G, and we're talking about 5G. And with each generation, our craving for data and higher speed has only increased. And trust me, it's going to increase, still going to increase, right? Statistics show that the mobile data that's currently being on the cellular network is already in units of exabytes, and it's only going to increase with the success of all this socializing networks like your Facebook, your Twitter, and hundreds of apps that are coming in today. It's tremendous. The traffic is almost like in astronomical numbers. So in order to keep up with this growing demand and have a sustainable growth is quite a challenge. Now that the dust around 4G is kind of settling down, let's talk about 5G. What does 5G expect out of us, right? 5G expects us to give a user experience data rate of around 100 Mbps. It wants us to give a peak data rate of 20 Gbps. It wants us to improve the spectral efficiency 3 times, reduce latency to 1 millisecond, and blah, blah, blah. But I want to focus on this aspect. Improve the network efficiency 100x times. Are you kidding me? No, right? Unfortunately, it's true. This energy efficiency in cellular networks is pretty much a growing concern among the telecom operators today, not only to maintain their profitability, but also to reduce the overall impacts on the environment. Hence, there is an emerging trend today to, bring in energy efficiency into cellular networks. So, in this regard, we are going to today discuss some of the research that's ongoing in this area, and we are going to also suggest certain techniques with which one can achieve energy efficiency. So our end goal would be to minimize the carbon dioxide emissions, to reduce the operational cost, to minimize the energy cost, and of course, have a prolonged battery life. So we're going to focus on our taxonomy. Our approach to this would be at 3 levels. We're going to focus on 3 aspects of green networking. Firstly, how to bring about energy saving at a device level. So we'll see how can we bring energy saving at a base station, at a protocol level, a very interesting topic of a self-organizing network called cell zooming, and etc. Later, we'll talk about how about bringing in architectural changes in the network using heterogeneous networks, and some of the very interesting future enabling technologies like smart grid and spectrum management, advanced antenna techniques, etc. So let's move. How much energy do you think is required to run a cellular network? In order to quantify this, we need to understand the energy consumed by different components of a cellular network. And our studies have shown that the base station consumes around 60% of the total power that's required to run the entire cellular network. On average, a base station consumes around 17 kilowatt per hour, and there are around 4 million BTS that are currently deployed globally today. So do the math, that's a lot of energy. So let us zoom into a little bit, dig deeper to understand which component in this base station is consuming so much of energy. And to our surprise, we found it's the power amplifier. The power amplifier consumes around 50 to 80% of the total energy, and shockingly, most of this is dissipated as heat, which in turn requires air conditioning for cooling, adding on to your energy cost. So one obvious conclusion we could derive out of this study is we need to bring in improvements in the power amplifier. In this regard, there's a lot of work that's going on. The current efficiency of the current deployed power amplifiers is in range of 5 to 10%, not more than 15. And for the RF applications, you need your power amplifiers to pretty much work in the linear region. So the linearity is pretty important for us. So we have power amplifiers which are based on this Doherty architecture. So this power amplifier basically uses a blend of your class AB and class C amplifier. So in the linear region, your class AB amplifier follows your signal. When it begins to saturate, your class C amplifier tops up, restoring your signal, thus improving your linearity. And with this architecture, the efficiency seemed to have gone up to at least like 30%. Also, the material that has been used to make power amplifier, it's been found that using gallium nitride-based power amplifiers are much better because they can withstand higher temperature and higher pressure. Also, there's an interesting study going on based on the switch mode power amplifiers. So what is this? In contrast to the analog RF amplifiers, switch mode amplifiers have their transistors which are switched on and off at an ultrasonic rate. So it's designed so that when the transistor is on, there's effectively no voltage that's formed across, and when it is off, there's no current that's flowing, effectively reducing the power that's generated as heat to very minimal. Right? So it's a lot. Also, you can use some of the algorithms in your Bayes RF module to improve the efficiency. So there is currently a lot of work going on. There's a lot of scope of improvements. And with these improvements, we could find that you can achieve at least 70% of savings in the base station. Next, we'll discuss a very interesting topic called cell zooming. Before I begin with it, let me make a small analogy. I mean, each room in our home is equipped with light bulbs, right? But we switch it on only when we need, when it's dark or when we need it. We don't keep all the lights of all the rooms on 24/7. Doesn't make sense, right? Now, can we apply a same principle to a base station? And okay, when I say base station, I'm referring to the cell towers. For those who are not from a wireless background, a base station is a base transceiver station. It's the normal cell towers that you see. That's what is a base station. So these base stations, they typically run on full power in peak hours as well as in non-peak hours, right? If you observe, there is the traffic load in cellular network is a function of space and time. If you see in the daytime, the traffic load is pretty much heavily concentrated in the office areas as compared to residential areas, and it's the vice versa during the night. Even otherwise, the data is much more consumed during the daytime as compared to night. So having a static cell size might not be an optimal solution for such varying traffic conditions, right? So when I say a cell is basically a geographical area that is served by a single base transceiver station, right? So what does cell zooming do? Cell zooming basically allows the base station to intelligently and automatically adjust its cell size, right? So let us take an example. We have here a network which is consisting of 5 cells. There are mobile users who are randomly distributed, right? Now imagine when all the mobile users start moving towards your center cell. What happens? It makes the center cell congested. Your center cell or your center antenna cannot serve so many so many customers. Hence, most of your request for your voice call or something gets, declined. So in this case, what can happen is the center cell can zoom in, reduce its power, and the neighboring cells can zoom out to provide the extended coverage. It's the same case vice versa. Imagine all the users are moving towards the outer cell. In that case, making the outer cells congested, the center cell can zoom out to provide the required coverage. Now, what if the users are distributed and the neighbor cells can effectively provide the required coverage? In that case, we can even put the center cell to sleep. And putting a base station to sleep conserves a lot of energy, right? So cell zooming is a technique with which one can achieve load balancing as well as energy saving. Having said that, yes, the cell zooming works only when you have adequate feedback that's given about the traffic condition, and the frequent fluctuating traffic condition makes this quite challenging to implement, but this is one of the promising solution to look forward to. Of course, this technique is expected to give us an energy saving of at least 20 to 40% in the base station power. And of course, renewable resources. You know that most of our base stations are powered using your on-grid power supply, but there are many regions which do not have access to this grid-based power system, right? So if a telecom operator has to go and provide service in those areas, he first has to roll out a power infrastructure followed by a cellular infrastructure. Instead, the base stations in such areas are typically run using a diesel power generator, which is of course expensive and also gives you emits a good amount of carbon dioxide. Statistics show that each generator consumes around 1,500 liters of diesel per month, and this results in an operational cost of 70 lakhs per year for the network operator, right? So you know that the diesel prices are only going to rise over a period of time, and this only means that you're not going to see a huge rise in your mobile phone bills. And none of us want that, right? So we need to find an alternative source to power our base stations. And in this regard, solar energy or wind energy can be seen as a viable option. Not just said, this has been done. Ericsson has implemented this in Africa, and Huawei has done this in Bangladesh, and India is not far behind. I think just a week back, I read that in a particular village in Rajasthan, the solar power telecom towers were installed. As a part of this digitization India, this is getting a very big push, and it's the need of the hour also. Powering our base stations with this alternative source can reduce our global diesel consumption by 0.4%, and that's a good number. Right, next we'll discuss on a protocol level. So we saw that radio consumes huge amount of power, so it only makes sense to put the radio to sleep to save some power, right? So our 3GPP standards, which governs this telecom, have tried to leverage on this aspect, right? So we've introduced some power-saving protocols called as discontinuous reception. So what is discontinuous reception? A discontinuous reception is where your device momentarily power downs, but it remains connected to the network. What happens is, each device, I mean, when I say a device, each of your mobile phones are mapped to a particular paging channel. Paging channel is one of the frequency channel on which you receive all your incoming triggers. If you're having an incoming call or incoming WhatsApp message or whatever is indicated by the network to you on this paging frequency. So what your device does is, it basically tunes to that frequency. It reads if it has something, if it has any information for it. If no, then it goes to sleep, right? The sleep period is already negotiated, pre-negotiated with your base station, and it's ensured that the base station will not schedule anything for transmission or reception when you're at sleep period. So if you see the dark blue periods, that's when your mobile station is actually tuning to those frequencies. If it finds no activity, it goes to sleep. It wakes up again, it reads, and if nothing, goes back to sleep. So it's basically like you're giving your, your device of, frequent shots of power naps, and power naps are good energy boosters, right? They save a lot of power. Next, we have topics on network planning, and Mahima is going to continue with those topics. Over to you, Mahima.
Thanks, Nivedita. Am I audible? Yeah, okay. So, as you know, she has set the foreground already for the energy conservation and what are the approaches. So now we talk about network planning. So what is network planning all about? This is the top level when we look at the cellular network. So it starts right from the network operator, how it's going to deploy the base stations, that means the various transmitters in the layman term, and how the connectivity and coverage will be provided to the users. So if we go into the details, these days we, like when the cellular communication actually started, it was kind of one transmitter, one high power transmitter, and covering a large area. That was the kind of model for the cellular system. Now, if you look at, it's been decades when the wireless communication has come up to this level now. Now when you see, it's not just one transmitter, but there's kind of multiple transmitters. So as you can see in the figure, that black one, center base station, is the traditional base station, which is a high power transmitter, providing a coverage to the bigger area. The big oval which you see is the bigger coverage area provided by that macro cell. Now, as an overlay, there are many small transmitters you can see in the figure, which are providing coverage in the small areas. So what are we playing around with this? It's basically intended to kind of provide coverage to the users which are either quasi-static or maybe pedestrian, or maybe people sitting like this in a conference room or at home, or maybe in offices. So when the mobility is minimal, then you can actually manage with a transmitter which can do the transmission at very low power. So instead of having a high power transmitter, you can that time manage with a low power transmitter. So that is what we tend to do in these days, and that kind of network we call it as heterogeneous network. Now here heterogeneity is in terms of what kind of small cell is that. That small cell could be deployed by the operator. It could be user deployed as well. It is as simple as switching on a Wi-Fi hotspot at your home. What do? You just plug it, switch it on. That's it, right? Same way, you can switch on a femtocell. Femtocell is nothing but just a small cell, which is an extension of the cellular services to you in your premises. So there are many such small cell possibilities which are kind of feasible and doable, which happens. So as you can see here in the figure, I'm not sure whether this really works. Okay. Okay, so here if you see, you have different backhaul connectivities like fiber, it could be coaxial, microwave, using which your bigger base station can talk to the small base stations. So it is the kind of headache of the operator, how that interoperability is maintained. But from the user's perspective, when you are in the coverage of a small cell, you can manage with a very low power transmission to connect to that antenna which is very close to you, compared to that bigger antenna which was far off. So we are more concerned about battery saving in our mobile unit, right? So here that resolves the problem. Now it's like for the less mobile users. But what about users which are kind of moving around, traveling, driving, whatever? For those users, it makes more sense to remain connected to the bigger macro base station. Reason? if you get connected to a small cell and you cross the boundary frequently of a small cell, you will have to undergo a handover. Switching from connecting to one small cell to another small cell, that incurs a lot of overheads as well as connection drop possibilities incur. To avoid all that, the flexibility is that network always facilitates high-speed users or mobile users in general, in literal sense mobile users, to get connected to macro cell. So this is how this heterogeneous network works. On top of it, how to make it work more efficiently, we have got many self-organized resource management techniques. One of this topic on self-organization I had covered in GHCI last year. So it's quite interesting because then, like Nivedita mentioned about cell zooming, all those things can happen and have to be enabled based on the dynamics. You don't know when users are going to get concentrated in which area. It's all about, it's random. It's all time-based. It's more often based on the seasons, day, night, timings, etc. So it has to be very adaptive. So whenever we have such kind of self-organized adaptive algorithms which keep track of the user density and their usage patterns and all kind of statistics, and then they play around with the resource management adaptive algorithms. Now, this is one example. If you see here in the figure, which has come up, it's an antenna system, which is a distributed antenna system. You can see on each floor in the multi, there is one or more than one small antennas. It is very similar to the access points you have in your offices. On every floor or maybe in multiple halls, you have those kind of things. So they all eventually get connected to one bigger antenna which is outside the building. So this is how you get better connectivity and you eliminate all the coverage hole issues normally which happens in indoor cases. Like normally in offices you have some areas where you say there is no signal in this area. We don't get coverage properly. So all those things get resolved. And this pattern is known as distributed antenna system. And so in all, we understand that with the heterogeneous network deployment, we end up having better capacity, much, much better coverage, and energy conservation at the same time. Okay, so next is, I'll touch upon enabling technologies. What are the new key technological areas or advancements happening which are favoring or helping us in conserving energy? One is smart grid. Nivedita already mentioned about the on-grid and off-grid system. So whenever the base stations are connected to on-grid, it's like an electrical system. It's a huge, you can say, large network of networks of connectivity of all the transmission lines and the transformers and the generators and the power stations and all those things. So basically it starts from very beginning from the power generation point to the plug point you have in your homes. You can consider that as a grid, electrical grid. So when base station is powered on, it is on a grid, electrical grid. But what I'm talking about smart grid is, what's smart about a grid? Smart here is, you have some kind of feedback mechanism. Feedback in the sense, you as a consumer can provide some statistics, some input to the grid about your power consumption usage, maybe about your foresight on the requirements, and you can adapt accordingly. So this will be kind of, you will have some energy meters installed, you will be paying only for the energy you use, and additionally, it helps when there is a power down kind of situation. When there is a complete blackout kind of situations, if you are connected to a smart grid, there will always be an alternate system to support you. You will never be, for example, if transformer blows off in your area, what happens? It's a blackout, right? Till the time it comes up. But if it is a smart grid system, there will be something else to back you up. Just like an inverter at home. You don't realize, right, ki the power is actually not there. So something similar is smart grid. Okay, next is the dynamic spectrum management. So this is something in context with the self-organized systems I was talking about. Here I'm mixing two things. One is the cognitive aspect and the dynamic resource allocation aspect. If you can see the left-hand side of the figure, that graph thing, you see the blue color boxes are showing the spectrum which is in use. That means which is already being used by the network and the users. In between, there is a white space. That is implying that, okay, before I say this, the spectrum allocation, how it happens. There are the spectrums, the bands, you must have heard about auctioning. Auctioning these bands happening, this company bought this, blah, blah, kind of news, right? What happens is operators have to buy, have to purchase and pay huge amount of money for buying spectrum. Spectrum in the sense they will be buying some specific bands and they have to specify the usage. It has to be only voice, only data, or it is mix, or whatever, broadband, or whatever it is. So they need to be very clear, and they really pay huge prices for the bands. Now, when this happens, the usage is not going to be consistent all through. You have purchased a band completely, but it is not going to happen that you are using it 100% 24/7. There will be opportunities when it is not being used. So this is what that white space here is indicating. So this opportunity is kind of, exploited. You try to identify where are the locations when the bands are not used, and you provide access to other users or maybe other networks which are falling short of resources. So this kind of arrangement is a cognitive radio technology. And this is that one aspect. Another is it has gone to a much higher level now, which I'll be discussing in the next coming up slides. But even this spectrum management aspect is likely to cover or give you a 50% saving approx on your energy consumptions. Okay, so next is the advanced antenna techniques. One glimpse I gave you already about the distributed antenna system. Here I talk about something which is more relevant to the 4G and the upcoming 5G cellular systems. So we have this LTE, long-term evolution. So these are some antenna techniques which are standardized by 3GPP to be used and deployed by the networks. One of them is coordinated multi-point transmission. You can see there is one user mobile shown there, and there are 3 base stations. So they are jointly doing the transmission to that user. You can imagine the amount of data it will be receiving and how efficient, because this is a wireless transmission happening. So there is a lot of multipath propagation and many losses in the go. But with such kind of coordinated transmission by multiple base stations, that means multiple antennas, we are not just increasing the reliability of transmission, but we are also increasing the capacity, the possible data rate which we can transmit in one shot. So this is one aspect. Another aspect could be that base stations, instead of doing the transmission in standard, typical omnidirectional pattern, they can beamform. That means they can kind of concentrate their radiations in a specific direction where they find a bulk of users. That means they are not wasting their energy unnecessarily, but they are concentrating, focusing their energy in the specific direction where users are there. This again saves a lot of energy. Further, 2 base stations can kind of cooperate and do the joint transmissions to a particular user. So it could be for the sake of redundant transmission. That means in the first case, it was doing a redundant transmission. In the second case, we see they are cooperatively doing the transmission. Half of the data one will send, half of the data remaining will send, kind of. Next, which comes up for the 5G, you can understand it has already started in 4G, but it is advancing towards 5G, this technique, which is full dimension, multiple input, multiple outputs. So you see in the first case, the antenna, you can see the beam being tilted. It's an electrical tilt. In the second case, you see it's a vertical beam forming. That means there is a beam on which you are concentrating your energy of transmission, but then that can be steered. You can have multiple beams. This implies if there is a high-rise building, a single antenna can kind of cover all the floors with multiple beams. And this is in contrast to the traditional antenna system. Those of you who are really familiar with kind of antenna system would know that there is a typical λ/2 kind of spacing required between 2 antennas. Now, to cover up a building or something, if I want an array of say 64 antennas, you can imagine how long that base station mount would be? More than 4 or 5 meters. And that's not a feasible base station mounting to be done, which goes long for 4 or 5 meters. On the contrary, this base station with the FD MIMO capability can actually do the beam forming and steer the beams. So it's a small antenna, multiple antennas tagged in a matrix form, and they have the capability to generate such beams in different directions. Do you get the point? So this is how the coverage can be maximized and at the same time, a lot of efficiency at the base station is achieved. Okay, if you look at the down figure below, it shows you a combination, how the horizontal beams and how the vertical beams are in totality providing coverage overall. Okay, so next is network virtualization and cloud. Must have heard these terms, I guess. Cloud is something which is at some place there. Somewhere you have a bulk of resources shared and then you are accessing those resources. How does it help me? You know, keeping every resource at yourself and then keeping it at some common place. It saves a lot of hassle because the data is not supposed to travel a long way. You just know one way to approach, where to get the data access and then come back. So it saves a lot of memory at all individual base stations. If you know that the common data which will be required is stored at one place where all base stations can access, instead of having a copy of the same data at all the base stations. So this is how it helps. And here there's a comparison. We are comparing the cloud resource management aspect and the traditional one. If you see the traditional one, it supports some, if I consider 2G, old scenario of GSM networks, it covers about 2 kilometers radius and covering only 12 to 36 carriers. On the contrary, if I'm working with Cloud RAN, which is shown here, I have a BBU pool, that is the baseband unit. So all those baseband processing are happening at one layer, and all the resource management aspects, that means the base station and the mobile units are as it is now. Only the baseband processing functionality is shifted from the base station to a cloud somewhere else. When we do this, we are actually able to support 1,000 plus LTE carriers. So that is a huge, huge kind of support. So capacity enhancement is extremely, just too high, because comparing GSM carriers and LTE carriers, switching from say 36 to 1,000 plus is just too huge. So we are in a position to support more users and provide them with a very good data rate with this kind of setup. So essentially the key for cloud and network virtualization is to decouple processing part and the transmission part. That is what we have done. All the baseband processing is happening in the cloud, and all the transmission related aspects are happening as they were happening before. So all the antenna units are below with us, and cloud is there somewhere to which we connect through via a high speed backhaul. So this is that real-time cloud for centralized processing, as we saw. And definitely it reduces your capital expenditure for the operator, operational expenses, and as a result, we pay less for the expenses. And it's highly energy efficient. The only catch here is that the backhaul is required to be high bandwidth and has to have a low latency. So this is still okay because we are actually having very good backhaul coming up with 5G here. And I already talked about this, distributed transmissions. So this is the big picture of how a network, virtualized network look like. You can see below that physical network infrastructure, transmitters, mobile units, the lowest one, that is where actual transmission is happening. If you go one step up, you see that there is a data center, content provider. There could also be some processing units connected there to which you will access. And additionally, you see that yellow box, virtual networks or MVNOs. That is a mobile virtual network operator. This is something very interesting because when it comes to spectrum for wireless communication, it is really a costly affair. And when you invest a huge amount of money in buying the spectrum and you're not able to use the spectrum optimally, you are at loss. I'm talking about you means network operators. So network operators are at loss and they have to cover it up for that somehow. Instead of that, There could be situations when the entire lobby of network operators can join hands, can come together via a third party regulating everything, and then they can lease their individual spectrums to this third party. Now, it is at the discretion of third party to assign resources to everybody judiciously. And of course, it's not going to happen that whoever has given the maximum number of spectrum or is going to be given denial of service kind of thing. No, that has some protocols, some norms. But if this third party comes into play, the best or the advantage of having the third party is the network operators, which are actually having users but are falling short of resources, can utilize the resources which were unused by other operators. So it is an efficient utilization of resources. You bring to a common pool and then share resources. Okay, so when we have this virtualized network, what happens is the intermediary thing, when you see those lines, they are all common network, common infrastructure. And the left side, right side is the users and the actual providers. So this is a kind of, network is one, but you are using it distinctly. So network virtualization is actually helping multiple operators to share the same infrastructure for providing different kind of services. And each operator may have its own, maybe using its one slice of the network. Because network infrastructure is huge. You are just using a part of it. And then you're happy because you are getting all that you wanted. And you will be paying only for what you have been using from that pool. You are not paying for the entire spectrum you have bought. And anyway, you're getting a lease rent from the third party. So it's all win-win. Now the virtualization requirement is, of course, deployment specific, and there could be a complete end-to-end virtualization, or it could be specific parts of the network which are virtualized. And then if I say conclude in final words, then I can see we have the cellular network like this. We have some small cells, we have some distributed antenna system, we have some combination of variety of small cells, I should say, some smart antenna techniques, some beamforming kind of aspects, and sitting on top of it, network virtualization. And if you understand it well to this point, it's very clear that the objective is not just to enhance capacity and coverage and the ever-increasing demand of the users and the expectations from the next generation networks, but to reduce the energy footprint, both at the transmitting point as well as at the user end. We don't want our battery to die very soon. We want it to sustain throughout the day without charging. So what do we need to do is, we need to exploit diversity. Where diversity? Diversity at both from the requirements perspective as well as in terms of challenges. And exploiting the diversity in networks as well as in functionalities. Because in network virtualization, what we did was, we were just splitting the functionalities. We are identifying the same roles, what is the same role of each element involved, and then we are trying to separate them, so that any kind of optimization to be done is unaffected and can be done independently. So no other thing in the network gets impacted by that kind of optimization at one level. Processing, so baseband processing, if you are playing around, you are only impacting the baseband layer, right? So that kind of, enables interoperability and provides a lot of flexibility to the implementing the research, new researches which comes into play, and new optimization algorithms which are being devised, because you just plug in at one place, you play around with that. If that works out, it helps completely the end-to-end system. At the same time, it gives opportunity to network operators. If they cannot afford to have an end-to-end virtualization, they can only go for a part virtualization. They can say only for the baseband processing, I want to have virtualization, rest all things I will do. That's okay. But then, anyway, whatever they do, they are also getting benefited, and as a user, we do get benefited. So, at the end, I can just say that we need to embrace all the diversity which we are getting from the challenges, from the requirements perspective and everywhere, and we need to embrace that, not just for higher capacity, but also to save energy. That's how we can have green cellular networks per se. So, thank you.
Thank you, Mahima and Nivedita, for in-depth overview of how green our network can be. We'll take questions for next 15 minutes.
Thank you, ladies, for a wonderful session. I'm Vasudha from Cisco. First question is for Nivedita.
Yeah.
So my question is for you. When you are talking about cell zooming, what aspect of the what aspect of radiation are you talking about? Are you talking about cell zooming on the beam width, reducing the beam width, or on the physical aspect of the antenna, or something related to the software side of it?
No, when I say it's basically like, see, when I say a cell, how do I define the size cell? It's basically my transmission power. So a transmission power of a base station is already predefined. During the network deployment itself, the transmission power is predefined and your cell size is also predefined. Now, the question comes is, do I need to cover that users? If there are no users in that area, do I really need to do it? No. So from a transmission perspective, I reduce my transmission power, reduce my coverage area, and that's how I zoom in or zoom out.
Okay.
So it's basically from a transmission power perspective at the base station.
Thank you.
No problem.
Ma'am, my next question is for you. You talked about 60% in reduction if you go for a smart grid, right? Is that 60% reduction on the existing macro networks or a in-building solution? Yes, smart grid.
So this is something which is in general. I mean to say, if it's like, because we are in a specific case, we are talking about those kind of cell sites which are off-grid. So we are comparing the case when you are serving them or you are making them operable by using diesel kind of things, compared to that if you put them on smart grid, how it works. And also comparing the case when you have the renewable resources of energy connected to your smart grid. So this is in totality talking about all those aspects.
Okay. You say take the smaller aspects of energy saving everywhere and put it to a smart grid.
Yeah, exactly. Because this is, actually 60% is also a kind of a tentative figure, because we cannot be very particular about doing this, doing that. This is something which has come up by the experiments and which where the deployments have actually happened in this case. So it is a test case which says that there is a high probability of achieving.
Reaching
Yeah,
that. Yeah,
correct.
that's a great number actually.
Yeah,
That's
true,
why-
true.
yeah.
Yeah.
Hi, this is Senthil. So my question is, some operator to increase the coverage, so they increase the transmission power, but it might be not, it's a harmful, right, sometime. So how this will help, let us say the beam forming. So for a particular direction, you are obviously increasing the power. It doesn't affect people, is it?
Yeah, so here when it comes to transmit power, see, this is very, very much math related, and it's very logical that if you have to increase the coverage, for example, if I don't have mic and I have to make my voice reach to the end of the corridor, I'll have to shout at the top of my voice. Same way, if I have to increase the coverage of base station, I actually have to increase the transmit power. But then this is not done randomly. There are governing rules. There are restrictions given by the government and the ITU and everybody. Like we have, this is the max TX power you can have for the operators. So that is the only, that is the limit to which they can increase the transmit power. They cannot go beyond that.
Okay,
Yeah.
thanks.
So we moved on from 3G to LTE for aspects like handover, to have a better handover, and it's completely packet data, right? So the functionality was moved from RNC to eNode Bs, and then you are talking about taking it to the cloud. Take all the eNode B functionality in eNode B processing into the cloud. How does it work out? I'm not able to understand what you're talking
Okay,
about.
I understand your point. See, if you have to conceptualize the idea, in case of LTE, the transition which happened, and if you're talking about the core network, of course, we have empowered the base station more in case of LTE compared to the previous generations. And the reason is we are trying to reduce the number of hops, because if you say, I do one processing here, and that too, and that is in tandem. It's not something which was happening kind of at a very high level the way it happens, or it is foreseen for network virtualization. But it was, we are trying to concise the network functionalities, and we have to provision in the foresight with which it was done for LTE was that we were supposed to kind of implement more of self-organization into the, we have to just kind of push for self-organization in the networks. And that becomes more possible when you have such highly capable eNode Bs at the base stations. Because if they know more, they have more information, they can talk to one another, coordinate better, and deliver better results in terms of self-organization, whether it is self-healing aspects or whether it is the efficient resource allocation aspects. But now when I talk about network virtualization, we are not going in the reverse direction, mind you. It's something which we are going one level above. It's like I'm now no more talking about just one network, one set of users and one operator kind of thing. No, I'm going beyond. I'm having a much top view here. It's like I'm sitting at the top and looking at all operators and all users in general. I'm trying to bridge the gaps and kind of, dilute the boundaries which are there in between.
Work together.
Exactly. So there, when you have this, that is why this MNO and all those things. So you have this mobile network operators coming together, joining hands. So now they have, instead of each operator running rigidly with their own pool and not sharing it with others, we have more sharing options. So when you start sharing here, why not share a cloud? Because then, instead of having a duplicate copy everywhere, and because this data, it seems like it's easy, but then when you have all those datas located multiple copies everywhere, save that data, and to retain that data, it requires a lot of power. You have to kind of have those amount of memories. You have to keep them safe. You have to provide them enough air conditioning and all those kind of things at all the base stations. If you offload them with reduced load at them, do only processing, remaining part is in the cloud. So they don't have to worry. And on top of it, it gives you more flexibility. For example, if you have to kind of, it's kind of optimization as well as it is more customization. For example, there is a low-end operator who does not want to play around much. He says, I just want some basic services. Fine. So you share, you will get all those services at the cost, whatever it is. On the contrary, if there is a kind of very, or you can say it's very, an operator who wants this, that, and is very ambitious, he can also play around with the same setup. So one infrastructure, one network, but it can cater to multiple use cases based on the requirements, and you need to pay only for what you're using. So it gives ample of opportunities for people to play around.
Okay. The replication of data, what data is duplicate? Do you have a
If you talk about data centers.
Okay.
So that way, if you see those kind of data, because it's internet, right? Internet it's all at the cloud. That's how you understand it. So those kind of data and the switching patterns which we have to happen, like all the routing algorithms, if you say. So they are all kind of, I don't need to have a copy of all the routes at my base station. I can just talk to my cloud and I can say, okay, this is destined for this location, what is the route? So they can run a very good algorithm, give me back the exact route which I should kind of follow,
Yeah. Thank you so much. That was nice.
We'll close this session. Thank you, Mahima. Thank you, Nivedita, for coming here.
Welcome.
On behalf of GSC, I want to thank you